Okay, so the slides that I have presented are more of kind of just bookkeeping for my own. They're not very organized as a story, so I hope to explain it by words fairly well. So I guess the main idea of what I'm looking at is surface chemistry and the impact of photo excitation on like their photo stability in these perovskite nanocrystals. So nanocrystals, they have a lot of surface due to their small volume. And on the surface, they usually have like passivating ligands of some sort. So in this case, what I'm showing in this figure is that for when there's a lead on the surface, there'll be an organic molecule bound to it. And then that's charged. And then there's a counter anion, which is nearby on the surface. And essentially, what I'm looking at is photo-induced degradation. So what happens is in the ground states, these coordinations would remain fairly stable. But if you shine the light onto them with like a little thunderbolt, that might cause the coordinations to break. So that you have chemistry happening on the surface, or you have breaking of bonds. So that's kind of the broad idea I have in mind. And then summarizing this is like potential energy wells. So what I have, so the general schema that I have in mind is that if our x-axis is some sort of reaction coordinate where you have changes in bond lengths, then y-axis is energy. And then essentially I'm considering 4 different configurations or that I have the models in. So I have a ground state where all the surfaces are coordinated. So that's 1 dot. I could, to mimic a photo excitation, I change the occupations to mimic an electron in the LUMO and a hole in the HOMO. So that'd be like another point on the diagram.
Aaron, sorry to interrupt. Should it be like vertical transition and then horizontal?
Yes. So then, yeah, the dot that I put, that would be like its equilibrium.
Yeah, let's make another dot because Mead is listening to us and we shouldn't confuse him. So that optical transitions are vertical.
Yeah, so yeah, photo excitation would be vertical, but in practice, for the calculations I'm doing, I optimize it so that it's the geometry changes in the excited state. If that makes sense.
Mm-hmm.
So those are for when the model is fully passivated. And then I go through and browse different configurations where if I remove pairs of ligands from the surface, and that would be these blue parabolas for when the models are in a ground state electronic configuration. and an excited state configuration.
Yeah, I probably should type questions rather than asking. I'll do it next time. There is a little, can I speak?
Mm-hmm.
So there is a little confuse that is okay inside the group, but for outside presentation, the energy, it shouldn't be homo and lumo. Some rigorous people may argue. So it like homo occupied, and then upper is electron is excited state for electron being transferred from homo to lumo.
Yes.
So the y-axis would be much better to label as total energy. Because if we literally mention energy of homo and luma, some communities consider that homo orbitals are having whiskers up and whiskers down, and luma are whiskers down. Like you understand what I'm talking about?
Yeah. So it'd be like there was actually
yes
homo like that.
Mm-hmm. Yes.
So yeah. So yeah, you're right. That's my y-axis is mislabeled. So those would be total energies.
Okay. Yeah, please continue, and I'll try to keep the format and ask questions in typed version.
Mm-hmm. So yeah, so essentially what I'm doing is I'm just computing total energies for different electronic configurations and configurations of defects on the surface of my model. And so it was giving me like the energetics, but then to describe the surface chemistry that's actually happening, I need to do experiments that somehow look at like the energy barriers between going from a fully passivated surface to some sort of defected state. And so that would be the like the activation energy for the ligand to desorb, comparing the excited states and the ground states. And my hypothesis is that this delta E will be smaller in the excited state configurations compared to the ground state configurations. So that it's easier for ligands to leave the surface when it's in the excited state compared to the ground state. And then that would involve doing molecular dynamics at various temperatures and configurations, which I've already done for one of the models. But then there's also the possibility of doing transition state searches as well, which haven't done yet, but I have some ideas we could talk about. So that's kind of the overview of the like research topic that I'm going to be exploring. And then the rest of the slides are just compiled data that I have so far from DFT calculations. So if there aren't any more conceptual questions about the research, I'll just move on to talking about the calculations and those results. So these are the three models which I have in mind for looking at the photochemistry. So for each of these models, the quantum dot is an inorganic core made of cesium lead bromide. And those are 2 by 2 by 2 unit cells, which make up the core. And then on the surfaces, there are pairs of charged ligands. And so the three ligand pairs that I consider are if you have carboxylates and ammoniums on the surface. So that's the blue box. In the middle, consider if you have ammonium bromides on the surface. And the model shown in the red box. And then the third that I'm considering is if you have cesium oleates on the surface. So oleate coordinates to the lead, and then cesium coordinates to bromine on the surface. So these are the three general models that I've been looking at and have optimized. And they're ground state geometries. So that's where I'll go to next. So these show the density of states for each of the models, and these are computed with spin orbit coupling. And then below them show the orbitals for HOMO, LUMO, and then a couple of extra states near the band edge as well. I guess the main takeaway is that for all these models, they have a clean band gap. So there's no trap states which show up, and then that the HOMO to LUMO transitions look like, look healthy, I guess. So it's, the HOMOs look like, imagine if you put a particle in a box, and then the LUMOs look like a charge that's delocalized over the entire box as well. So their electronic structures look good to this point. And then another thing to compare for each of the models is the absorption spectra, which gives an idea of what the band gaps are for each of these.
Aaron, would you please give us a little more time to enjoy the orbitals?
Yeah. I can zoom in too.
Maybe just comment other similarities and differences, and whether all of the models follow the expected trends of like SPD or like number of nodes, or there are any deviations from like ideal three-dimensional box.
Yeah, so for most of the models, I mostly focus on like the HOMO LUMOs, because those are the easiest to interpret from what VASP outputs. And generally for those look, they have like a spherical symmetry or an S-type, meaning that there are no like nodal planes in them and that they're delocalized throughout the entire box, like throughout the entire inorganic core. Where for the HOMOs, the orbitals are located on halide p and lead s orbitals, whereas for the LUMO, those are all mostly lead p orbitals.
Okay, so the envelope functions for the HOMO and LUMO do match the expectations in all three cases.
Yes.
And for next orbitals, there are some deviations.
Yeah, so for I guess all these are the HOMO -2 orbital.
Mhm.
And the general expectation would be that there's some sort of p symmetry, or so that in the very center of the box, there should be no or very little orbital density in the middle, and that most of it should be like the sides of the box in this case, since the model is so small.
Mhm.
You can see in the middle panel, if you look at the HOMO -2, that looks fairly orbital. And I get a marker. Kind of has a dumbbell shape.
Mhm.
Whereas for the other two orbitals, it has like half of the dumbbell,
Mhm.
which I think has to do with the way that VASP writes out the orbitals. Oop, wrong drawing tool.
So if one would make a superposition of several orbitals, as one is doing in the TDDFT, then likely the lowest excitations will show the SPD trends. Do you think so?
Yeah.
Okay.
And
What about LUMO +1 and LUMO +2 for the middle case? For methylammonium bromine ligands.
so LUMO +1 will look the same as this,
Mhm.
this one,
Mhm.
because each of them, because it's each band is twice degenerates, so it's
Mhm.
so you have the same orbitals. And for I'm trying to remember, I think I remember looking at it, but I can't remember if it doesn't look as nice as this HOMO -2. I guess, yeah, I can go back and look at some of the other higher excited states to see if they look all right. But I guess when I was browsing through, my main concern was whether this LUMO orbital looked like all the LEDs had p orbitals on them, because that's a sign that the model is healthy. It can go on to further steps.
Okay, let's go ahead.
Mm-hmm. And so we have the density of states. And then another observable we usually look at is absorption spectra. So this plot in the middle is just an overlay of the absorption computed for each model, where the color codes for the lines in the boxes match up. And I don't have a lot to comment on the moment. Well, I guess the first thing is that usually you expect the lowest transition to be fairly intense compared to other transitions in the absorption spectra. You can see that for each of the models that the absorption onset has a high oscillator strength or has a high peak. So that's usually an indication that the models are healthy. And this blue one is less just because I think I used a different broadening parameter compared to the other two. But you can see that for all of them, there's a bright onset, and then there's like a weaker tail at the higher energy from like 2.4 to 2.6. Then once you get to higher energies, there's a broad absorption bands. I guess the curious thing when I first made this plot was that there seems to be a wide, like a variance for the absorption onset. So you can see that this red curve, which is the ammonium bromide, has a band gap of like 2.1 EV. Whereas the models that have oleates on the surface have band gaps to like 2.4, 2.5 EV. And I'll mention that now, but I think in a couple of slides I'll come back to what I think is the reason for this wide variance of band gaps between the models. And so what I'm going to show next is structural characterization of the models. So what I did is I computed radial distribution functions and angular distribution functions for specific like atom pairs. So that's what I'll show next. So the top two rows are radial distribution functions, where the very top row is radial distributions for the inorganic core. So the red lines are essentially show bond distances between lead and bromine. in the core. And the green line shows bromine-bromine distances, but I won't talk about those as much. And then I also, so that's the top row. The middle row is looking at coordination distances of species on the surface. So the red line is lead oxygen bond distances. And the blue line is coordination between the ammoniums and the bromine. And then the very bottom row is an angular distribution. So it's the angles between the lead bromine in the inorganic core. So what I'll focus on is just looking at the changes in the core structure between lead and bromine. So on the left shows the radial distribution functions, where each of the colors correspond to the model boxed. And then the right hand side shows angular distribution functions. So the x-axis is degrees for like 3 points. So 90 degrees is a right angle between the bonds, or between the three species, and then 180 would be like a line between the bonds. So the interesting thing is that you can see in both of the plots that for the models that have oleates on the surface, so the green and blue curves, they have a fairly wide distribution of bond distances and also have a fairly wide distribution of bond angles. Whereas for the ammonium bromide model, it's fairly symmetric. For the radial distribution function, it's fairly centered around one peak at about 3 nanometers. And if you look at the angular distributions, it's fairly centered around 90 degrees. So that means that for the ammonium bromide model, like all of the bond distances are kind of like an ideal octahedral coordination. Because for an ideal octahedral, there's like all the bond distances would be 90 degrees. Whereas the model with the oleates, it seems to break that perfect octahedral so that the bonds are more narrower in angles. So these were all just a bunch of observations I made while compiling all this data. And I guess I'll skip this, but this just is same idea, but it's just coordinations of ligands to the surface. I guess I was looking through one review paper that Dimitri sent me out at one point in time. It was some group where they mostly focus on analytical tight binding models of perovskites. And they made a comment in their review papers that matches the observations that I found from the DFT modeling. Whereas if you have like strain in the octahedral, or if you have bond distances that aren't perfectly 90 degrees, that you should see an increase of the band gaps for the models. So if you have angles deviating from 90 and 180 degrees, you should see band gap increases for the same bond distances. And so I think that kind of explains why for the optical spectra, why the ammonium bromide had a lower band gap than the cesium oleate or oleate and ammonium models, where their band gaps are like 2.4, 2.5 EV, and their bond angles show significant deviation from 90 and 100 degrees. Whereas the ammonium bromide has the smallest band gap, but has the most symmetry or most symmetric bonding. So the main takeaway is that the carboxylates on the surface create lattice strain. And so I just thought that was an interesting observation when I was making these models and just going through their observables. And then if there aren't any questions about this, I'll move on to the next slides, which looks at the orbitals for the lowest excited state configurations.
So you have supported with this data that volume of the anchoring carboxylate group is bigger than any other ligands, and therefore it creates strain and makes a blue shift of transitions.
Yes. Whether they're bigger or if it has to do with the bonding, I'm not exactly sure what it is, but it's just a observation that's when these carboxylates are on the surface, there are changes in bond angles between lead and the halides, which has an impact on the optical spectra.
Okay.
So it's a structure to property relation.
Okay.
So that's the main takeaways from just looking at the ground state electronic structure, and all the models are fully passivated. So the next slides will look at the excited states structure with all of the surface sites passivated. And I guess this one shows two of the models. This must be an old set of slides. I have the third one somewhere too, but I guess the main takeaway is that, I guess first, if we look at the density of states, we can see for each of the plots that there's some color in the conduction band where you would expect LUMO to be. And then there's a lack of color in the valence band where you expect HOMO to be. And that just indicates that this is like the lowest excited state that the system can be in, which is an approximation for a photo excitation. And again, I got some, I plotted orbitals to accompany the density of states figures. And overall, the same trend stays the same for what the orbitals look like. So HOMO has orbital density on the lead S and halide P orbitals, and it's distributed throughout the box or delocalized. And for the LUMO, it's most of the electron density is on the lead P orbitals, and they're mostly spread out or delocalized through the entire model. I guess yeah, I guess the thing to say is that with the lowest excited state, the character of the orbitals remain the same. So there's not a very drastic change in the orbitals or the density of states. There's not very much like moving around of the energy bands.
And it can be rationalized that overall change of density upon excitation is negligible compared to total density in ground state. Therefore, change in the potential is also very small, and set of orbitals is quite similar to those in the ground state.
Mm-hmm. Yeah, I forgot to mention these. So these are optimized in the excited state.
Mm-hmm.
So it allows the structure to find the minimum.
Okay.
So I guess we've looked at the ground state and the lowest excited states with fully passivated surfaces. And the next set of data will look on what happens to the orbitals and the density of states when I remove pairs of ligands from the surface and optimize the model. And I guess just to give an intuition for why I think the ligands have to leave as pairs is that if I just look at comparing total energies for the different ligand pairs, and that in most of the cases, the total energy is reduced when they participate in some chemistry. Because if we just remove one of the ligands, it will still remain charged, or that even the nanocrystal will start to have an imbalance of charge because one is plus and one is minus. So if we remove both from the surface, that helps keep charge neutrality. And that when we remove them, and that the ligands will participate in chemistry, which make each of the products neutral. So to summarize, it's just that when the pairs leave the surface, they reduce their total energy. So there's some sort of driving force wanting them to leave the surface. So this set of slides looks at the ground state electronic structure. And if I remove ligand pairs from the face of the crystal, and by face, I mean like the very, well, I guess I have them circled in the orbital pictures. So where I have the red circle, I removed the surface species that was coordinating to that atom, and then an adjacent counter ligand.
May I ask?
Yeah.
So are you removing by making an offset describing little departure from surface, or you actually removing a pair of ligands from the simulation cell?
So I remove them from the cell completely.
Okay, so it cannot be part, then it cannot be part of a single set of potential energy surfaces. It's basically a different system. I'm not criticizing, I'm just learning.
Right. Well, yeah, I guess, yeah, in this case, it wouldn't be the overall potential surface. So essentially, it's just it gives me one of the points.
Mhm.
So in this case, it would be the ground state defect potential energy. It gives the total energy of that configuration,
Mhm.
but it doesn't give the like the like the spring constant or whatever to make the parabola.
Okay.
Yeah, so I manually remove ligand pairs and then re-optimize the models. And then these are the density of states for the re-optimized models that have surface defects or are uncoordinated. And in this case, we can see that with the removal of one ligand pairs, that there's no like signs of trap state formation. Or if we look at the orbitals, the HOMO and the LUMO orbitals look they look the same as if the surfaces were fully passivated.
Aaron, may I add a comment?
Yeah.
So when you are recomputing the electronic structure of this cube, three-dimensional box with removed ligand, one may consider to make an analogy with problems from textbooks when one is looking on the particle in the box with little change at the bottom. and then it considered analytically as a through perturbation theory as either deficiency or extra kink in the potential, and then all energies can be evaluated analytically. So it looks like in one of the dimensions, your box does have this little kink in the potential, and changes to the energetics could be assessed analytically if needed. Likely it is not needed, but just in case.
Mm-hmm.
Okay. Sorry for interrupting. Please continue, and I'll try to follow the protocol and ask questions by typing rather than interrupting. But let's keep going.
Yeah, so I guess I don't have too much more to say. Is that, I guess the only other thing I'll say is that the other expectation is that if there was a trap state, that we'd expect to see more of the density localized near where the defect is. But so far in this case, we haven't seen any orbitals that show that character. Okay, I thought I was on a lag for a second. I guess one of the configurations to look at would be the same face defect, but in the lowest excited electronic configuration. So that's just on the to-do list, but I haven't gotten results that far yet for these models. So that's why this slide is blank. Mm-hmm. And then the next one we'll look at is ground states electronic configuration, but we have an edge defect on the surface. And by edge, you can make it out in the middle panel. If you look at the HOMO -1 orbital, where there's the red circle, that's where I define the edge defect as. So it's like one of the edges of the box. And we see essentially the same thing, whereas even with the defect, that the charges are fairly delocalized throughout the inorganic cores. And there's no real changes in the density of states. So then the last slide I had for looking at defects is considering the lowest excited state configuration, electronic configuration, where you have edge surface defects. And this is a model where we start to see the formation of surface trap states from visualizing the density of states and accompanying that by looking at the orbitals. So we can see that in the valence band where the HOMO is, so that looks still fairly what I would expect, except it seems on one of the sides that's the charge isn't as delocalized through the entire model. But if you look at the conduction band and the LUMO +1 orbitals, you can see signs of trap states where the electron density is definitely skewed or trapped to where the surface defect is.
Aaron, may I ask verbally?
Yeah.
So I'm a little bit lost in notations. So in few previous slides, you were looking on the ground state of the models where a pair of surface ligands is removed.
Yes.
So it was ground state. And the density of states was very similar to ground state of the intact model. Right now, the slide is labeled lowest excited state. Is it so like is it truly and if it is lowest excited state in the density of states, I do not see inversion between HOMO and LUMO.
So it's
Like there is no void with white with absence of the solid color in the HOMO. It looks more like negatively charged system from this DOS.
yes, I think that might just be an issue of pixels.
Okay,
So
but
it's
it is intended to be a white void in at -3 electron volts.
yes.
Okay,
So it's and check the calculation, but I think it could just be that the thermal broadening just doesn't leave a lot of white space under the curve. Yeah, so I guess I know it's more of a comment. I don't really know how to phrase it, but comparing the ground states models to the lowest excited states with the defects, like we see, at least for this one case, for the lowest excited state, that we see signs of trap state formation, whereas with the ground state configuration, those seem to look more healthy, no defects. So it's, I guess a statement or a question is whether like occupations of the excited states helps like the trap state form, or it stabilizes in a sense.
So in the it's similar to mechanism of polar information in upon promoting electron to the like excited state, there are rearrangement of lattice that lead to localization of charge near the defect.
Right. And so it's hard to generalize with just one model, but it's just something I'm keeping in mind as the other or as data from the other models comes in. I guess that's the last slide that I have looking at different configurations of electronic occupations and surface defect sites. So this is just a reminder in my slides to possibly think about doing or trying to look at the reaction barrier for the surface reaction. And it's something I'll have to talk to Yulin about once I get far enough to think about building models and what's the best way to do it. I think from the last meeting that we had, the idea I think Dimitri was saying was just to consider like a 2D slab. In VASP where, oops, it's hard to make more than one line.
There is a draw option, and it is much better draw the third one in the menu. Not the insert figure, but draw. In the main menu, like home, insert, draw, design. So the third one is draw. No, it was the text below the red line. If up next. Yeah.
Oh, there we go. Ah, there we go.
It looks like a bicycle. The rider.
Yeah, I guess some sort of design like this where we have, because I've never done it before, but from what you guys were saying last time I presented, that like a cluster would be too much, would be too heavy of a calculation.
Yeah, and slab would be cheaper for sure.
Mm-hmm. It would just be a way to approximate the height of the barrier for the model of interest. Yeah, those are mostly ideas at the moment, but I'll have to talk with Ewan about the best way to make the slabs and then how to actually run these modules in VASP. But what I do actually have data for is molecular dynamics for one of the models in various electronic configurations and temperatures of running the molecular dynamics at. And so I guess one of the challenges was trying to find a way to quantify the surface degradation during the trajectory. I guess what I figured was to utilize radial distribution functions again. So the top two lines are just the formal ways to write out the radial distribution functions. And the second line shows that if you, well, if you look at the area under the RDF curve, that should be the total number of atoms in the system. So during the,
Aaron, I apologize for interrupting. Let's discuss the first equation briefly, the very initial one for G of R.
yeah,
So N, what is N of R? Is it like number of neighbors as function of distance from the central point?
yeah, so it'd be, you considered like yeah, it's like the number within a certain like radial distance. So with the change of radius, what's the change in like the number of species within that like incremental change?
Okay, and if you take derivative over, distance, it will be like number of neighbors on a certain sphere, right?
Yes. Mm-hmm.
And then you divide it by the surface of a sphere analytical. So to normalize, to avoid the quadratic growth with distance, right? Otherwise, it will, if you do not do this normalization 1 over r squared, this if you keep only dn over dr, it will grow quadratically because sphere becomes bigger and amount of neighbors on each next sphere is bigger.
Mm-hmm.
And if you do this normalization, it will be approximately like if it is a random liquid or gas, dense gas, it will be like a flat line. And if it is a solid, it will be like sharp teeth.
Mm-hmm.
Okay.
And then yeah, solids, they'll just be peaks
Mm-hmm.
where the atoms are.
Okay.
So I guess the main point that I'm trying to get at with this slide is that you can't, if you do RDF functions for like each time step of the trajectory, like it's not very useful if you consider the, like looking at all the atoms in the system, because that doesn't change. Or, well, for our simulations, it won't change the total number, but you can look at the changes in coordination numbers, or what I call this N bonds. If you just consider integrating up to like the coordination distance between the species.
Okay. So if some bonds are broken, the distance become bigger, and these neighbors go into a different sphere and are not in this R bond threshold.
And you should, and that would mean that you lose the area up to that bond.
I have an immediate question. Will this number of bonds be integer number, or will it be normalized to actual number of bonds, or it will be a small number changing in like fractional, like 0.1, 0.001? What will be the units for this number of bonds? Can one expect that if in the model you have one bond broken, then this delta n bonds will be changed by 1, or it's you're not sure?
Rigorously, yes, it should change stepwise.
Mhm.
If well, I'll show you in the next slide, but if I took the time to figure out what the actual normalization should be, like we should know at the initial time zero how many bonds there are,
Okay.
what the coordination number is, and then how that changes, and it should be integer stepwise.
Mhm.
But just for proof of concept, I didn't look at the normalization. I just had the same roughly initial, like initial state for the number of bonds, and then just seeing what the trend is over time.
Mhm.
So the application of this would be to the models, looking at the coordinations of this carboxylate, the leads, or if I was rigorous, the number, I guess the potential number of surface bonds would be 108,
Mhm.
because there's, yeah, if you just look at the stoichiometry, you can get that. And then the same with lead bromine. If I consider that on the surface, like it should start out as 54 and then change throughout the trajectory if there are changes in coordination. For the model that I looked at the change, the number of these oxygens coordinated to lead at the surface for different electronic configurations. So GSMD is ground state molecular dynamics, and ESMD is the lowest excited state, doing the trajectory for, oops. And then running the MD at different temperatures.
Mhm.
And so you can see on the left that all the models, they start out at roughly the same number of coordinations. It's not 64, but it's
It should be 108, right?
right. Ideally, yeah, ideally it should be 108. If all of them bonded in this way, but sometimes like there's only one oxygen, but those are fine details. But the main thing to see is that for the ground states at 300, and you can see that there are slight fluctuations. So you can see that initially there's a decrease, increase, decrease, but then also an increase. So it seems that there are
Bonds are broken and then regained.
more, right. So it stays near the surface, but it's popping on and off to whatever my threshold value was for our bonds, which I didn't make strictly this bond distance. I made it like a slightly higher tolerance value. But anyway, back to the figure. So green is the ground state at 300K. And then the black is the excited state configuration at 300K. We can see that there are fluctuations, but over time, there do seem to be permanent loss of these carboxylates coordinated to the surface. And if I pulled up the YouTube video, like it would, like you would see these signatures visibly as one of the ligands going very far away from the surface. And then if we keep the same electronic configuration, but just reduce the temperature to 77K, we can see that there is we actually see a gain of some coordinations to the surface and then kind of fluctuates over time. But comparing the red and the black curves, we can see that temperature significantly influences the photo degradation as well as the electronic configuration, comparing ground state versus excited state. So I guess my main statement would be that this black curve is an indication of photo degradation, where it's easier for ligands to leave the surface when the model is photo excited compared to when it's in the ground state. So this seems promising to characterize the surface chemistry of the model. And the last, the most exciting figures would be to look over the dynamics. Specifically looking at the photoluminescence characteristics for a couple of the different models and seeing whether the trap states has a significant influence over the photoluminescence properties as to whether, like if you form a defect, whether it becomes quenched and completely dark and useless as an emitter, or if there's like an in-between scenario where it's not totally detrimental, but there are signatures of trap states being detrimental to the emission in these models. I guess, yeah, that's the last slide that I have for this. And then this would be the goal of working through all these models, is trying to characterize the excited state dynamics.
Okay, please join me in giving a round of applause to Aaron. It's really interesting research with a very bright finding at the end. Let's go to the questions and answer session, and maybe just go from the questions that were typed in the chat line and give Aaron a chance to answer them. So I would like to welcome Professor Krzyzewski, based on the suggestion from David Graupner, who mentioned at the beginning. Welcome to the meeting. Feel free to join anytime you find it interesting and participate in the discussion. Okay, so the first question was from Yulun. Is it a photolysis or pyrolysis?
I guess I've never seen the word photolys before. I guess, yeah, it's photo-induced decomposition. So I guess, I don't know if it would be pyrolysis, because that's due to heat. Actually, I'd take that back. So it's photothermal degradation. So I guess it would be a combination of both, because from this figure, we can see that changes in the electronic configuration, which comes from the photo part, can change the occupation numbers, but we can also see that like the heat or thermal contributions also contribute to the degradation. So I guess it would be a case of where it's a combination of both processes.
Okay. Yvonne, are you satisfied with me telling I was going to address that XD? I have already forgotten what we were talking about. Mead, if it is something relevant, please repeat the question verbally. If it is not important, just message. Not relevant. Okay. Next question from Yvonne. Is the reaction coordinate physically meaningful when comparing two systems? I think it deals with like slide number 3 or somewhere at the very beginning when you did a schematic diagram.
Right. I guess, I think there is a way to make it physically meaningful, but it's still fuzzy in my head as to exactly what that would be. So the reaction coordinate would have to be something involving like a surface atom, and then one of the ligands that leave the surface. But it gets complicated because since I'm, at least in these models, considering multiple molecules leaving, so you have multiple distances. So it's, I guess I would say it's hard to compress into a one-dimensional.
As a very crazy suggestion, merging the last and first slides of your talk, would it be like a very crazy hypothetical idea to use number of bonds as a reaction coordinate and then write the potential energy surfaces as function of number of bonds?
It's a provocative idea.
Okay, next question. I think it was from me. Other pathways for transitions between red and blue potential energy surfaces? Like if one draws this diagram, is it legitimate to tell that one is considering transition from, well, optically one can go between lower and upper red lines, but and lower and upper blue lines, but is there a mechanism to go between red and blue?
I guess the picture that I have in mind is that like this barrier would represent the energy needed for like the molecule to remove itself from the lead on the surface, or for the surface ligands to detach themselves. So the barrier would be like the energy required to do that. But then the final state it would have to represent like the combination of the inorganic like cluster itself and the detached ligands.
Okay. And continuation of this question, for the way you define things, is it necessary to keep all ions inside the simulation cell, or one can draw the same diagram for the models when you remove a couple of ligands and recalculate things.
Well, it makes sense to me to get the total energies from the way that I did it, because like I compute the total energies of the defected model, and then I just add in the energies of the like the products of the leaving groups. If that makes sense. So it's this, so each like a state has the same number of electrons, same number of ions, but they're just the way that they're arranged in space is different.
The next question is from David Graupner, who already left for his teaching duties. And I think it is continuation of the same subject. Would they need to be kept in the simulation cell for the reaction coordinate to be legitimate?
I think to get, like if I wanted to get the barrier, yes. For just comparing total energies, it's not required.
Okay. Then we go to the probably next slide, and I see the. Can you please go to the next slide?
Yeah.
Yeah. So I think the question is from myself, naming for 3 models, because this pair of ethyl, ammonium, these chemical namings can be provocatively complicated for non-chemists. So I wonder if one can call them these 3 cases like OO, IO, OI for organic, 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 inorganic, inorganic, organic. I'm not sure that it is the best way. Maybe the just pure chemical naming is fine. Just bring it. Next suggestion is from Yulun. He's asking, would it be useful to next slide, to accompany it with PDOS?
Mm-hmm. Yeah, that's something that could be done.
Okay. Next question from myself. I think it was discussed like whether the Luma +2 for middle model, would it have the p-type? And you mentioned that it's not exactly p-type, but some maybe. Is there any structure to property signatures that this ideal, like not ideal, but most expected shape of orbitals for ethyl ammonium bromine model is given the brightest spectrum in the next slide.
I think I'm putting it together now. So I think, yeah, PDOS could help show like the contributions to HOMO and LUMO. And that's for the like larger band gap models. It's like their HOMO and LUMO should show bonding to the carboxylates.
Mhm. Okay. So it is not, it's only the hybridization. Next question is from Yulun, and it is why the onset of absorption is different. What is the contribution of surface ligands and surface lead bromide atoms to the frontier orbital?
Yeah, so I think the absorption onset is due to like the bonding geometry, which I described earlier.
Mm-hmm.
And then so yeah, I think we talked about this a little bit, but yeah, these, I guess what I call these X ligands, so carboxylates and bromine, they both, well, I know for sure that the carboxylates, they do show some contribution to the HOMO and LUMO just from past models looking at this. And the bromines would too. I'm just not sure to which, like, to what extent. Yeah, that would be some figures that I should put together to accompany this data.
Okay. Then I'll skip a couple of comments that we already discussed. And then next question is from Yvonne. There are two types of surface ligands, A and X. To find the effect of X, we compare red and blue. To find the effect of A, we compare blue with green. Maybe in future, keep the reference blue in the middle panel.
Yeah, I think he's talking about the color of the outlines.
Right, to have the, that I suggest to call OO, organic in the middle, and two types of organic, inorganic, and inorganic organic on the sides. Right?
Mm-hmm.
So it's like two-dimensional space. Which of the ligands is swapped between organic and inorganic? Okay. Then I think we are going through few slides without questions to the binding energies. $11. Yeah. Would it be interesting to subtract charged and neutral total energies, and would it be appropriate to call it energy of charge transfer or energy of neutralization? Would it be any? Would it be a realistic, observable, or only an abstract concept?
Well, I think it might be a good approximation to like what the barrier of the ligands leaving the surface would be.
Mhm.
Because yeah, this would be the energy, like roughly, of the molecules on the surface. So when they're charged, but when they're neutral, it's like they're in a lower energy overall. So like this energy difference, at least in my mind, gives an idea of what the barrier is.
Okay. So the next, I'll skip my own question. I think it's not needed now. The next one is from Yvonne, and it deals when to the slide when you, it deals with this one, and then few slides later you declare plans to practice nudge elastic bands. So question of Yvonne is, what is the reactant and product for the nudge elastic band calculation?
Mm-hmm. Yeah, the reactants would be like the ligands that are naturally on the surface. And then the products would be like the protonated versions. I guess so on the very left, like when the ammonium donates its proton to the carboxylate, like that would be the ending product. And this one I do observe in the molecular dynamics. Like when the charged version of this carboxylate leaves the surface, it steals a proton from ammonium nearby, and then this acetate just freely floats in the simulation box.
So in some sense, it is a surface proton transfer reaction.
Mm-hmm.
Proton transfers and then both depart.
Mm-hmm. Yeah, because it's like the most favorable binding to the surface is when they're charged. So if they ever become neutral for either thermal or interacting with the environment, if they become a neutral species, they're likely to leave.
So it could be two-dimensional potential energy surface. One dimension is proton transferring from one to another ligand, and second dimension is center of mass of this pair of ligands departing from center of mass of the quantum dot.
Mm-hmm.
Okay. Next question is about your number of bonds as function of time. Yes, slide 20, I think. These results. So you're comparing ground state, excited state, and there is method that Yulun is practicing and Mid is practicing TDSMD, where system is being frequently converted between ground and excited. Hypothetically, would the degradation go quicker if one does this TDSMD, flipping between ground and excited? Would the black line decline quicker?
I don't know. I guess my gut reaction would be it would go slower, because when it's in the excited state, it's like always in the on. position?
There is, I would like to argue on this statement. So your idea is that if we are 50% of time in the ground state and only 50% of time in the excited, then reaction will be 50% less active. Will be less chances to go for the reaction. But when we are jumping up and down between potential energy surfaces, we keep coordinate unchanged in the instant of transition, but the kinetic energy accumulates from at each cycle. Because the potential energy surfaces have offset, each time we jump, it comes to the non-equilibrium position and gets additional acceleration. So it accelerates here when it goes to ground. Then you go up, it accelerates in opposite direction, and each time it gets more and more velocity. So kinetic energy increases constantly, and it is not like abstract thought. It is objective observation. So possibly, likely, if one jumps between ground and excited, it will break more bonds.
Mm-hmm.
And I would like to suggest that Aaron and Yvonne have private conversations through emails and maybe exchange ideas and maybe codes to for mutual benefits. Okay. The thing that I would just wish in the wish list is to, maybe you presented in one of your previous talks, is the absorption or emission of the model where ligands are removed. So it is expected that it will be much less bright.
Mm-hmm. Yeah, I guess. Yeah, it'd be easy to do or to add.
Yes. And if you are targeting the high impact journal, it is the main experimental observable. Through the photodegradation, the model becomes less efficient absorber and emitter.
Mm-hmm. Yeah, I think. Yeah, I just haven't looked at that yet because it's like for the defect models that I've shown, they looked fairly healthy.
Mm-hmm.
So I'd expect those ones to be more or less still bright. But it's when I see orbitals that look like trap formation, that's a signature. Those ones will be more dark.
Okay. Okay. I do not see any more questions in the list. So if there are additional emergent questions, please feel free to ask to Aaron. If no, please join me in thanking Aaron for really interesting presentation. It's